My name is Kurt Wise. I'm a professor at 𝘎𝘕 University in Cleveland, Georgia. I'm going to talk about a little bit of my training in geology. This goes back into the previous millennium. But when I was learning my geology, I was taught that certain features of the geologic column require long periods of time to form. Solid rock is eroded very slowly. Valleys are eroded very slowly. Winding rivers require very long periods of time to form. Mixtites are sediments with at least two different very big difference in size particles. These are formed by glaciers that require long periods of time. Deltas are formed slowly, etc. There was a long list of geologic features that I was taught require very long periods of time to form. Now, soon before I finished my undergraduate work, Mount St. Helens exploded in western United States, and we learned in the course of studying things that occurred during that event and after, that things that I had been taught required very long periods of time to form were in fact formed at Mount St. Helens very rapidly. Rock was tens of feet of rock were eroded in the matter of just a few hours in some mud flows following the event. Cross-bedding, graded bedding, rhythmites, mixtites, these are things that formed in seconds in various parts of the explosion itself. Deltas, in the matter of just a few years, 13 years or so, very large deltas formed downstream of the sediments, and so on. In each one of these cases, the things that I was taught required very long periods of time to form could form very rapidly under catastrophic conditions such as those at Mount St. Helens. An interesting question I asked myself not too long ago, now that it's been more than 40 years since the eruption of Mount St. Helens, why didn't that change geology? Because as far as I can tell, geologists are still being taught the very same things I was taught, that these things here require very long periods of time to form. Why didn't the events of Mount St. Helens change geology? I thought they would at the time. I thought, wow, this is impressive stuff. This is going to transform geology and move it more in the direction of interpreting the stratigraphic column in terms of catastrophe. But it didn't. Why? That's what I want to address in this particular lecture. I think the answer goes back, all the way back, to the beginning of geology. Geology as a discipline is the youngest, arguably the youngest of the sciences. It really didn't form until about 200 years ago, a little bit more than 200 years ago. The first geological society was the Geological Society of London, founded in 1807. The first textbook, if you wish, of geology was Charles Lyell's Principles of Geology in 1830. It is the events, of course, of these first few years in the beginning of the 19th century that established the teaching pattern for geology that we still enjoy, if you wish, today. And it was, of course, Charles Lyell in particular that would argue that the things that I referred to in a previous slide were things that had to and did, in fact, form very slowly. And I'll give you a few examples of, I don't have time to go through all of the examples that I had there, but I got a few representative examples. Most of the rest are answered in very much the same way. So let's consider one of them, which is graded bedding. How is it that graded bedding is formed? First of all, what is it? A graded bedding is where, as you look up in a rock unit, you see different sized particles at different levels in the rock. Typically, what's called normal graded bedding would start with large particles, and then they get smaller and smaller as you move up in the rock. Reverse grading would be where you've got small particles going into large particles. That's unusual. Graded bedding is more common. Well, we see the graded bedding in rocks, and we can also reproduce graded bedding in even just a jar. If we just take a bunch of sediment of different sized grains and mix it all together in water and shake it in a jar and let it settle, it will typically settle in a graded bedding fashion, where the largest particles, the heaviest particles fall out first, and then subsequently the lighter and lighter particles, till you end up with a bed of reverse grading. Obviously that occurs in just, it can occur very quickly in just a few moments, according to our experiment there. And in rocks, we can also not just find graded bedding of a unit, but we can find a cycle of graded beds. A graded bed from coarse to fine, followed by the next bed going from coarse to fine, followed by the next coarse to fine. This repeated graded rhythmite pattern, rhythmic, repeated, graded, where each rhythmite level is itself graded. We see these in rocks, not just in a whole large unit, not repeated above it, but also in repeated fashion. And we see the same feature in modern beaches. So if you cut down through the layers of sand on a beach, you will find graded bed, followed by another graded bed, followed by another graded bed. So rhythmites we find on beaches. We find graded bedding on beaches and rhythmic graded bedding. So given that, and we know that beach sands, they're sampling the formation of sand over a long period of time, they in fact produce these graded beds in a series of, let's say, a series of storms. And the storms are separated in time from each other, so that graded bedding on beaches with tides or with storms are things that require long periods of time to form. So it has been traditional to kind of ignore experiments like this, where you can do it very quickly, and look at things in the real world. Charles Lyell in the 1830s said, hey, this is what we see in the real world. So when we see graded bedding, rhythmic graded bedding, we have come to associate those things with the slow forming beach sands. So what was taught back in the early 19th century, and what is still being taught today, is that when you see graded bedding, think in terms of, this is what the students are taught to do, this is what I was taught, you think in terms of a beach depositing sand over a long period of time. Now granted, it is accepted, I mean, people understand that you can produce graded bedding very much more rapidly under catastrophic conditions. For example, a tsunami can produce a series of graded beds. Each surge of water coming onto shore can produce a graded bed. A pyroclastic flow at Mount St. Helens can produce a graded bed, or did produce graded beds in the matter of seconds. We know of large floods coming out of canyons, opening out into open areas down below, that they produce graded rhythmites, and then do that in the matter of minutes to hours. The avalanche at Mount St. Helens, in fact, produced graded beds in literally seconds of time. So we know that graded beds can form other ways. The conventional world knows that as well, but these processes are in the present day rare. They are, tsunamis don't occur very commonly. They're separated in time by long periods of time at any given location. Volcanic eruptions, sure, they can produce these things quickly, but they aren't occurring every day. And at any given place, they might be separated by thousands of years from one another. Floods also can do this quickly, but they're separated from each other in time and space so much that when you see graded beds in the record, the best thing to do, so the argument goes, is you go to the normal processes of forming graded beds on beaches. So it's because of the fact that catastrophism is a rare phenomenon in the present that we interpret, or we're taught to interpret, graded beds as taking a long period of time, even though they can be produced quickly. Another example is laminar bedding. This is in contrast to graded beds, where you have a change in size of particles up the bed. Here you don't, but you have very fine layers, horizontal layers produced in, or seen in, a rock. We see that also again on beaches. So beaches without tides and without major storms, or evidence of major storms, have very nice laminar bedding. So again, you're taught to when you see laminar bedding in the record, think in terms of a beach. Even though we know that mud flows and pyroclastic flows and avalanche at Mount St. Helens produced laminar bedding, these things are rare, so they are to be largely ignored. First order assumption is that when you see laminar bedding, you are to think in terms of slow beach formation. There's a mixtite as another example. Again, this is a rock made of at least two different sized rocks, sand-sized rocks with boulders in there. That's a mixtite. It's a mixture of rocks of different sizes. We know in the present that glaciers, which are carrying rocks, in cross-section of glacier, you see a bunch of debris in the glacier. It's carrying debris up to a place where the motion of the glacier, let's say down the hill of a mountain, is equal to the rate that the glacier is melting away. So it's carrying debris up to that point, and the melting causes it to drop the material into a pile at the end of the glacier. So glacier coming up from above, and it drops it into a terminal moraine at the end of the glacier. And if you look at that material, you find that it is a mixtite. It has got large particles, large boulders that are carried in the ice down to the moraine, as well as ground up boulders that have been made into sand and so on. A mixture of sand and boulders, a mixtite. So again, what you're being taught in the class, geology, glaciers are always occurring. They're continually creating the mixtites at their termini. So when you see a mixtite, you are to think in terms of a glacier. And a glacier works slowly, takes a long time to develop a mixtite. So, in fact, when you see a mixtite in the record, you're taught to interpret that as having taken a long period of time by the deposition of ice. Now, we know that mixtites can be generated quickly. They certainly are formed in avalanches very quickly. But again, avalanches are the sorts of things that are not occurring as often as glaciers are creating mixtites. So what you're taught is that even though mixtites can be formed rapidly, most of the time they're probably formed by glaciers. So for 2 centuries now, we've been taught that rhythmic graded bedding, laminar bedding, and mixtites are in fact formed very slowly. The student is taught that if you see rhythmic graded bedding, you are supposed to see in your mind, or interpret in your mind, that hours, days, or longer are required to create the graded beds. And if you see laminar beds, you're to think in terms of the months and years it takes for beach sand to accumulate. And if you see a mixtite, you're to think in terms of the slow, gradual motion of glaciers to produce mixtites at their termini. So that's why it's what I call a geological myopia. The students are taught to see only the long period of time, slow depositional modes for each of these rock types. Not just those, but all of those in that list. Well, what happens if we've got a unit that we see in the rock record which actually doesn't quite fit that? You're taught to, I go to the record, here's a bunch of rocks here, and these are rhythmites. When you look more closely at them, they're graded rhythmites, so you'd think in terms of, well, that's got to be daily tides on a beach or something like that. But in this particular photograph, notice the person for scale here. These things are huge. These are not the little rhythmites that you find on beaches. They're just too big. Plus, these things are found several hundred miles from the sea. There are land fossils in the sediments, not sea fossils. And they're very thick. So seem to be too thick for tides. They're not near the ocean where tides are, and they don't contain fossils that you would expect at the ocean. So even though, so the student who's been trained to say, oh, well, graded rhythmites would mean a tidal shoreline, they're going to want to interpret that as tidal shoreline, but there are things that just don't fit. So what do you do when you encounter a rock that doesn't fit? Well, what sets in is what I call geological myopia. Either the student says, I just don't see the problems, or I'm skeptical of, okay, it seems that I need to consider something else other than a tidal shoreline, but I'm a little skeptical of those others. So at best, they're willing to consider the catastrophic origin of things, but they remain skeptical because of the way they've been taught. Now, historically, there's an interesting challenge that came to this way of teaching that came about because of a person by the name of J. Harlan Bretz. By the way, J is not abbreviation for his name. That's actually his first name, J. J. Harlan Bretz began doing field work out in eastern Washington. And beginning in about 1822, about the age of 40, he thought he saw evidence of an extremely large flood that came across the state of Washington, portrayed here, that in fact water covered a significant part of the state of Washington before pooling and making its way down what is now the Columbia River gorge, and perhaps cut that gorge. Now, this way of thinking in terms of a catastrophe, a very large flood, a flood of this kind of dimension, this is way out of the ordinary here. This is not the way Charles Lyell argued it 100 years earlier. So J. Harlan Bretz, in beginning to make arguments for this, found people were opposing him. And he had a hard time. It took 50 years for him to finally convince the geological community that his intuitions back in 1922 were in fact valid. And it's one of those few examples where somebody actually lived long enough to see his ideas accepted. He actually lived to be nearly 100 years old, and so he was actually old enough, he actually lived long enough to receive a prize from the Geological Society of America for the work he did over 50 years trying to argue for this flood. The idea was that he didn't know anything about the source of water, but there must have been some source of water, he argued, from somewhere to the east of Utah that broke through and cascaded across the state of Washington to the sea. Again, it took 50 years to get the idea accepted, and the reason that it wasn't accepted right away was because of geological myopia. There's actually a fair bit of evidence for these things. For example, all the way back in Montana, there's evidence of a very large lake. Shorelines of the lake can be seen just above the city of Missoula. There's a big M made on the side of the mountain that's made from basically shoreline boulders that have been collected into one place and painted. It's right above the University of Missoula, University of Montana there in Missoula. You can see the old shorelines that indicate there's a very large lake up there. Also at a place to the northwest of that, there's a narrow place where it's apparent that these look like ripple marks, and they are. But if you look closely here, you see that those are trees, and the trees are shading a homestead that's sitting there. These are huge ripple marks, enormous ripple marks. They're so large that before the use of an airplane to fly over the area, they really can't be seen from the ground. You drive across them, and it is this funny little, but they're so large that it took a long time for people to see them, and it was hard for J. Harlan Bretz to argue that they were really ripple marks. But if they're ripple marks, then the rules of sedimentation are that the depth of water to produce a waveform like this underwater, the water has to be 5 times the depth of that unit. So the water's got to be filling this valley. This is a desert. And so the idea is that there was a large volume of water, a river that was more than 100 feet deep, moved through this region at a very high speed in order to produce these kind of ripples, moving from the lake towards Washington. Downstream, we have those rhythmites I referred to before, the Touché formation, that are the kinds of rhythmites that are formed in floods when you narrow the water through a canyon and then the canyon opens up. It actually, the water comes out in spurts and produces these rhythmites, very large rhythmites. It explains why they're large, very thick rhythmites, and why they're a long ways from the sea. So that was further evidence of this event. In the middle here in Washington, we've got potholes. We're familiar with potholes, but look at the scale. There's a blue pickup truck for scale. These are huge potholes. These are potholes that are a couple hundred feet across in some cases, indicating that there's very large boulders, that water moving across the surface is rotating in eddies and whirlpools, and the rock is boring its way through very solid basalt rock. Also, large areas in here completely stripped of soil, no soil at all, no vegetation, and the whole surface is like somebody shaved off everything that couldn't be picked up by, shaved off everything that water could pick up and take away, as if water had flowed across this entire area, scraping everything off the surface. These are called the scablands of eastern Washington. Very large, thousands and thousands of square miles of area have been scoured down to bedrock. And we've got ripple marks, large ripple marks, again, a house for size, a road for size, extremely large ripple marks that indicate that floodwaters were moving from the northeast to the southwest. Very large boulders, there's a person for scale, that were carried by this water. And then once it got channeled into the, as it's going towards the sea here, it cut the valley that the Columbia River runs through today, and it cut very steep sides on that valley so that you have waterfalls all along this valley. The streams that used to come straight into the river now have to drop into the valley carved by the by this event, such as Multnomah Falls, a famous falls here along the Columbia River. I mean, we can marshal all sorts of evidences, which finally 𝘎𝘧 Bretz was able to do, to make a very, very convincing argument that there was, in fact, a very large flood that covered a third of the state of Washington, at least, in the past. And so in that case, it makes sense then to accept a catastrophic origin for the graded beds that we find in the Touché Formation. Now, to be fair, and to those who are resisting this, it's also true that radiometric dating indicated that this is more than just 1 year of deposition. There's more than one radiometric year represented here in these deposits. But again, if they really are rhythmites, they are rhythmites from a single event, so they would be less than a year. So that would suggest that maybe something's wrong with radiometric dating, which of course the conventional world doesn't accept. And perhaps accelerated decay in the past would then accommodate all of this into something less than the year that this event probably occurred. The erosion of 𝘎𝘧 Bretz's flood, it's not the flood of the Bible. It's a much smaller, itty-bitty flood that followed the flood, but it nonetheless almost certainly would have been less than a year in activity. So that would suggest that radiometric dating needs to be compressed to accommodate it. It took 50 years to accept a flood of this size, the Missoula floods, and most of the resistance to that, the reason it took that long, is because of what I call geological myopia. There's a bigger flood found to the south. So whereas you've got evidence of a lake that's of this size up there for the Missoula floods, you have evidence of lakes of this size and a very much larger canyon cut than the Columbia River Canyon down here. To the south of this, we have a bigger flood. Evidence that lakes drained and moved water to the southwest to the ocean. We have evidence of in the 𝘎𝘧 Formation. The 𝘎𝘧 Formation is actually lake sediments, and the lake sediments are sitting at 5,000 feet elevation. There shouldn't be a lake there because right now there's a drain for that lake that would prevent water accumulating in that lake. But if you filled up the Grand Canyon, this could easily fill with a mile deep of water. And there's evidence here with snails and clams and so on. There really was a lake here. So we have evidence of a lake having been there. We have evidence that the lakes that we find here, that you can see in satellite photos by different vegetation than the surrounding green vegetation area, that the water left those lakes very rapidly, scouring the edges, leaving no debris at the base of these cliffs, whereas cliffs are continually eroding and dropping what we call talus down on the floor or on the sides beneath. These are completely clean, or nearly completely clean, of talus, suggesting that there was once water in here, and the water, as it left this area catastrophically, it carried most of that talus away. What little talus we see in the present would have fallen down since whenever this flood occurred. And then we have scablands in this area as well, similar to the scablands that are found in Washington, except that they're bigger and occupying a much larger area than we see up there in Washington. And then we have a canyon known as the Grand Canyon that is cut through a natural dam, bent up rocks that would have backed up water to create these series of lakes up above. The Grand Canyon is the spillway for those lakes. We have down below the canyon, downstream of it, rhythmites in the Salton Sea region. And if you look at the geologic age of the lake sediments up above and the rhythmites down below, they are very close in age, but the rhythmites are younger than the lake sediments. And if you calculate the amount of rock that's missing in the scablands and in the Grand Canyon, there's that equivalent amount of rock found in the Salton Sea rhythmites. So we have evidence of lakes draining out through the canyon, eroding the canyon in the process, and dumping debris out in the Salton Sea area. We have what creationist Steve Austin calls a smoking gun here. We have evidence of this event. Now, again, there is geological myopia resisting this, but it's not entirely myopia because radiometric dating, again, gives you millions of years for the dating of the lake sediments and for the sediments down below. But again, you put all these evidences together, this looks like a single depositional event. Probably took a few weeks or so to occur, best estimates, best guesstimates, I'd say, which, and of course that would be accommodated if in fact radiometric dating is based on radiometric decay rates that were much higher in the past. Then perhaps again we can put the evidence of this flood within a single year. It took 50 years to accept the Missoula floods, and we still haven't accepted the evidence that the Grand Canyon was eroded in that fashion, in spite of a large amount of evidence that indicates that these sediments should be interpreted in terms of a single catastrophe. There's something even bigger that's even more difficult to see. It took 50 years to accept the Missoula floods, still haven't made it on the Grand Canyon stuff. There's something bigger than that. Let's pull back and look at the entire United States from coast to coast. So here we have a satellite photo of the whole thing. Now remember, when we see laminar bedding, or we're seeing graded bedding, we're supposed to think in terms of a beach. Okay, so looking at the satellite photo, where's the beach? At this scale, can you see the beach deposits in the United States? Well, let's see. Well, look down here. There's some white stuff along the edge of Florida. Perhaps that's beach material. Let's enlarge it to see if in fact that's true. When you enlarge it, you realize that this isn't beach material at all. These are houses. This is human development. So you still can't see the beach. Well, maybe that white stuff along the edge there, maybe that's beach. Let's blow it up again. Lo and behold, no, this stuff is not. This is still housing developments and so on. It's astonishing, actually. You can see from satellite photos how much we've changed the surface of the planet. Perhaps the beach is over here and not over here. Let's blow that up. Most of it is houses, but there's a line right there of beach. There it is. There's the sand. So at the scale of the continent, you cannot see beach sand. I mean, there's a ridiculously small amount of beach sand along the very edges here. No beach sand anywhere else. So in the present, beach is producing an unseeably small amount of sand. So what do you do when you see a sandstone spread across the entire continent of North America? We have a sandstone that is found from Maine all the way into Mexico, all the way up into the Arctic, everything but the yellow stuff here. This is a sandstone that covers the entire continent. Did this form, even if you see lamination and all of that stuff in it, did this form in a beach? I don't think so. This just cannot be beach sand. Beach sand can't even be seen at this scale. How could it produce something of this size? That's unthinkable. We shouldn't be thinking in terms of a beach to explain this sand. Plus, we have evidence within the sand that currents are moving the sand from the east to the west across all of this. For example, there are crystals of zircon crystals, uranium crystals, that are identifiable as coming from the Smoky Mountains that are found in Death Valley. And so at the time this sandstone was deposited, currents are ripping material off of the eastern United States and carrying it across the entire continent. There would be no Mississippi River or anything like that. It's crossing all current river basins. The whole region, it's like a moving ocean moving across North America at an average elevation of about 1,000 feet above sea level. And out here in the west, it's up to 15,000 feet thick. It's 5 miles thick. 2,000, 5,000, 3 miles thick. It's 3 miles thick off the edge of the continent. Is this a beach? There's no possible way this is a beach. It looks like an ocean moved across the North American continent. By the way, there's marine fossils in it. And that's not all. Let's pull back even further. This particular sandstone is only one layer in a graded rhythmite section in North America. So this one layer is this yellow layer right here. Underneath it is a conglomerate layer, big boulders. On top of it, there's a shale across the entire continent, and above that, a limestone. And then we repeat the sequence. You got a sand, followed by a shale, followed by a limestone. It's a fining up, it's a graded bed that is thousands of feet thick. And then another one above that, and another one above that, and a fifth one above that. We have 5 graded beds across the North American continent that are, and you can see it here on a Kasuna chart. This is a bunch of columns of rock at various places in the U.S. This is the central U.S. You can see the sandstone as yellow across here. Gray is shale, and on top of that, the blue is limestone. Then we have sandstone again, limestone again, sandstone again, limestone. We have these graded beds, 5 of them. They're thousands of feet thick. These are certainly not from anything like a shoreline. And the rock underneath this sandstone here shows up as this orange stuff way down here, has boulders in it greater than 1 mile in diameter. So this is thousands of feet thick with boulders in it that are huge. No way they can be moved around on shorelines. I would suggest, and the rhythmites contain, all of these sediments contain billions of marine fossils on the continent, a minimum of 1,000 feet above sea level. Tides? If so, it would be tides that cover entire continents and would wipe out everything on the planet. It would be tides that create a global flood. Now, to be fair, radiometric dating says these rhythmites were deposited over 500 million years and weren't part of a single depositional event. On the other hand, those same radiometric methods indicate that seismic waves took tens of millions of years to cross the continent. Some really cool rocks that we know have been fragmented by shock waves from earthquakes. And the shock waves moved across the North American continent, creating these shattered rocks as it went. And radiometric dating of these rocks indicate that that shock wave took 100 million years, pretty close to 100 million years to cross the continent. Shock waves don't do that. Shock waves move at the speed of sound, 500 plus feet per second. It's not going to take millions of years. It's only going to take hours to cross the continent. So that would suggest that these radiometric methods are based upon a period of time when radioactive decay was a million times or so, even more than that, millions of times faster than it's occurring today. And if you apply that back on the ages for the whole thing, it suggests that perhaps all of these rhythmites were formed perhaps less than a single year. And that's what it looks like. We need to consider these as a unit, as evidence of certainly each graded unit should be considered as a single unit. So the whole thing would suggest there is a global flood. If it weren't for geological myopia and the radiometric dating issue, all things continue as they were from the beginning. That would be geological myopia. The evidence for a global flood would be obvious. The evidence for a global flood across North America is profound. Is that going to be accepted? I don't expect it's going to be accepted anytime in my lifetime or my grandchildren's lifetime, because it took 50 years to get this tiny little Missoula flood thing accepted. Still haven't accepted the quick origin, catastrophic origin of the Grand Canyon. To think in terms of a global flood on this planet, geological myopia is going to keep people from believing that for probably a very, very long, for generations to come.